Hello, welcome back to Shine Sleep Stories. Tonight, we're going very far away. Not just in distance, but in time too. We're going to the beginning, or at least as far back as the light allows us to go. We're going so early in the story of the cosmos that most of what exists today wasn't even conceived by the universe itself. There were no galaxies in the known sense. No spiral arms gracefully gliding in the darkness. No elliptical giants slowly moving in clusters of their own making. Just warmth, hydrogen, and the soft whisper of gravity touching matter. This is where our story begins. And it begins, not with a discovery, but with an absence. The absence of what we expected. There was a silence in the silence that should have been in the data, but instead, impossibly, there was light. To understand why these first galaxies are so strange, we need to know what the universe looked like before them. Before galaxies, before stars, before any structure, in the beginning, and by beginning, we mean the first few 100,000 years after the Big Bang, the universe was not a place of objects. It was a place of conditions. Everything was so dense and so hot that even atoms couldn't combine. Protons and electrons moved freely, independently of each other, floating in a cosmic mist. Light couldn't travel very far. It was absorbed and scattered almost instantly. In those early moments, the universe was opaque. Then, about 380,000 years after the Big Bang, something changed. The universe expanded and cooled enough. Electrons slowed down. Protons caught up with them. Hydrogen atoms formed for the first time, a simple, silent, most fundamental state of matter. And with these atoms came transparency. Light suddenly found a place to go. It began to flow in all directions and has traveled ever since. We call the echo of that moment the cosmic microwave background. It is the oldest light we can observe. It is the trace of that first great illumination. But in the moments that followed, the cosmic dark ages that lasted hundreds of millions of years, the universe was silent. It wasn't empty. Hydrogen and helium drifted slowly, pulled here and there by the hidden hands of dark matter. Small fluctuations in density areas, slightly denser than their neighbors, began to collapse under gravity. Slowly, patiently, matter began to accumulate. The first stars ignited perhaps 200 to 400 million years after the Big Bang. We didn't see them directly. They were enormous, blue, extraordinarily bright, and in just a few million years they exhausted their fuel and exploded as supernova, seeding the surrounding gas with the first heavy elements. We call them population 3 stars. They were unlike anything that formed afterward. Then came the second generation, stars born in the gas, slightly enriched by those first explosions. They are cooler, longer-lived, and more diverse. And around these stars, in the regions where they clustered, the first protogalaxies began to form, small, irregular, lumpy. Stars and communities of gas and dark matter were slowly colliding, merging, and growing. That was the story we believed. The universe started slowly, patiently evolving, and complexity slowly unfolding over billions of years. And then we looked more closely. It all began quietly, as it often does. A survey of a telescope designed to map the faintest objects in the farthest corners of the observable sky was scanning a patch of sky billions of light years away. The light it collected was moving when the universe was young, stretched thinly by the expansion of space, reaching infrared wavelengths that the human eye could never see. One of the thousands of faint spots catalogued in that survey caught the attention of the researchers analyzing the data. Initially, it didn't seem very impressive. It was just another spot of ancient light. But when they measured its spectrum, the fingerprint of wavelengths that shows what something is made of, and how fast it's moving away, they felt something was wrong. The redshift was extreme. This wasn't just unusual. Many objects showed extreme red, but what the spectrum revealed was even more disturbing. This object wasn't a quasar. It wasn't an energy burst from an active black hole, nor was it a side effect of the instrument. It was a galaxy, a real, structured, massive galaxy. And this galaxy existed more than 13 billion years ago. At that point, the universe was less than 1 billion years old. Researchers reviewed their measurements. They rechecked them. They investigated for calibration errors, contamination from environmental sources, or anything else that might have misled the data, but the signal remained solid, clean, consistent, and disturbingly real. What they found looked like an extremely mature galaxy for its age. It wasn't a baby system still gathering its first stars, it was something big. Something built. From every direction they measured, it looked like a galaxy that had grown over billions of years. Asterisk to understand why this discovery is so perplexing. It's helpful to know what galaxies are supposed to be. Astronomers classify galaxies in many ways: size, color, star formation rate, chemical content, but the most fundamental distinction is shape. And shape tells a profound story about a galaxy's history. Asterisk spiral galaxies are what most people imagine a galaxy to be. They are filled with flat, rotating disks of stars, gas, and dust in broad arms. They are active places. Their arms shimmer with young stars rising from cold molecular gas clouds. Our own Milky Way galaxy is a spiral. The same is true for our closest large neighbor, the Andromeda Galaxy. Spiral galaxies are considered relatively young from a galactic perspective, or at least they are still building themselves up. Asterisk, elliptical galaxies, however, are different. They are smooth, round, or oval structures, and are mostly composed of older red stars. They contain very little cool gas, very little dust, and almost no new star formation. These are the galaxies that astronomers sometimes call red and dead. Not a disparagement, but an expression describing their defining characteristic: the quiet glow of old light. These galaxies have exhausted their star-building fuel. They have entered a period of cosmic retirement. Asterisk, the standard model of galaxy evolution suggests that most large elliptical galaxies formed through mergers. Two or more spiral galaxies collide over billions of years, and their structures are overturned by the force of the encounter. Their gas is ejected or depleted. Their stars are scattered into a new, smooth shape. This is a slow process. Building a large elliptical galaxy takes time for smaller galaxies to form, for them to gravitationally influence each other, for the merger to complete, and for the new structure to settle. Asterisk, all of this takes billions of years. So when astronomers found the smooth, rounded profile of a large elliptical galaxy already in the early universe, one that was both massive and rapidly forming new stars, they ran into trouble. Asterisk, it looked old. It acted young. It seemed too big to be forming so quickly. But it was. However, it didn't have billions of years. Let's accept this for a moment. This early galaxy, let's call it Paradox, which doesn't have a very nice name, had several characteristics that shouldn't have been found together in a single entity. First, its mass. It contained roughly the same number of stars as our Milky Way, maybe even more. In a universe less than 1 billion years old, bringing together that much stellar mass would require an incredible amount of raw material. To be forced to collapse under gravity and coalesce into stars very quickly. Our models of structure formation meticulously built on decades of observations and simulations predicted that this would take much longer than the present time. Second, its shape. Paradox had the smooth, rounded contours of an ancient elliptical galaxy. There were no scattered star-forming regions. There were no complex filaments of dust and gas. There were no arms distorted by a recent collision. Everything about its appearance indicated that it was established, ancient, and complete. Third, and here's where the interesting part begins. It was still producing new stars. Hundreds of solar masses of new stars were emerging every year. That's an extraordinary rate. Our Milky Way galaxy forms only a few solar masses of new stars each year. Galaxies that produce new stars at rates like Paradox's are generally young, complex, gas-rich systems in the early stages of their lives. We're not talking about smooth, large, seemingly old structures. Fourth, chemical richness. The light from Paradox contained spectral signatures of heavy elements: carbon, oxygen, iron. These elements can only form in the cores of stars and then be dispersed into space by supernova events. The presence of these elements indicated that Paradox had previously gone through many generations of stellar birth and death. Stars had formed, exhausted their fuel, exploded, and enriched the surrounding gas, and this seemed to have happened not all at once, but over many cycles, all within the first billion years of universal history. This shouldn't have been possible. Researchers studying the paradox concerning astronomy generally avoid emotional pronouncements. Science progresses slowly, and scientists generally shy away from explaining the impossible. Yet, in calmer discussions, the same phrases kept popping up in the margins of papers and in conference speeches. Something is wrong. There's nothing wrong with the data. There's nothing wrong with the instruments, but there's something wrong with the story. After the first signs of these impossible early galaxies began appearing in old observational data, the scientific community adopted cautious skepticism. Old telescopes had limitations. Redshift measurements could sometimes be confused with strange objects. Perhaps mass estimates were wrong. Perhaps star formation rates were being misinterpreted. Then, the James Webb Space Telescope opened up the sky. The JWST was designed to see the early universe with a clarity that previous instruments couldn't match. Its mirror was large enough to collect light in extraordinary quantities. Its ability to precisely detect ancient light arriving with redshift was unique. When it turned its golden gaze to the deep reaches of the sky, to the dark regions where old telescopes had only seen the faintest traces, it didn't confirm the standard narrative. It made everything more mysterious. Within months of its initial deep-field observations, the JWST recorded surprisingly advanced, extremely large, and structured galaxies in the early universe, making the gap between observation and theory insurmountable. One galaxy became 5, 5 became 20, 20 became a certain type that shouldn't exist at all. Yet each time more galaxies were encountered that were present in the sky, each one carrying an inconsistency with their very existence. These galaxies had more mass than the Milky Way. When the universe was only 600 million years old, some had already stopped producing stars, even before the universe had begun to form them as it matured. They had peaked and ended star formation before it should have begun. The JWST revealed the chemical complexity of these objects in unprecedented detail. Predominantly elements, multiple star belts. Long-lived galaxies have a distinct characteristic: compressed timescales, periods that should normally be very short. The models were flawed, not just slightly, but significantly. When observations challenge a theory, scientists don't immediately abandon it. That's not how science works, and it shouldn't. Theories are built on vast amounts of evidence. They aren't abandoned because of a single anomaly or a few. They are kept under pressure, tested, expanded, and revisited. But the anomalies of the early universe, the impossible galaxies, revealed by the JWST and confirmed by independent reviews, were not just a dozen. There were hundreds. They were systematic. They were repeatable, and they were inconsistent with the standard cosmological model. This wasn't a marginal case, it was fundamental. So theorists began to ask more difficult questions. The first category of explanation proposed encompasses the galaxy formation process. Perhaps we underestimate the efficiency of the early universe's gas transforming into stars. Conditions in the early universe were quite different from today. The gas was in a purer state, lacking the heavier elements found in the modern universe. In the absence of these elements, the cooling pathways might have been different. The gas could have condensed faster or disintegrated less, leading to the formation of stars of extraordinary mass in short bursts. There's another question about the first stars, the population 3 stars we mentioned earlier. We've never directly observed them. However, theoretical models suggest they possessed immense mass, perhaps hundreds or even thousands of times that of the Sun. Such stars would live fast and die violently. Within a few million years of formation, they would explode as supernova, enriching the surrounding gas with heavy elements and instantly triggering new star formation. A single generation of population 3 stars in a confined region could likely have triggered the rapid formation of the entire subsequent stellar population. The second category of explanation involves dark matter. Dark matter is the invisible skeleton of the universe. It's the matter that makes up the majority of galaxies and galaxy clusters. providing the gravitational wells into which normal matter falls and condenses. We know it exists from its gravitational effects, but we've never directly detected it. Our models of how dark matter behaved in the early universe are inferences, not direct measurements. Perhaps these inferences are wrong. Perhaps the early dark matter rings were denser or more clustered, or behaved in ways that allowed gas to fall in and stars to form much faster. A slight change in how dark matter clustered during the first few hundred million years could have drastically affected when and how quickly galaxies merged. Asterisk. The third category concerns black holes. We're talking specifically about supermassive black holes at the centers of the largest galaxies today, including our own. The mass of these objects ranges from millions to billions of times the mass of the Sun, and they are thought to have grown slowly over billions of years, fueled by falling gas and stars. But what if some formed first? What if, under the extraordinary conditions of the early universe, massive black holes formed directly from the collapse of massive gas clouds, completely bypassing the star-forming process? These hypothetical objects' direct collapse, black holes would have provided centers of extraordinary gravity, pulling gas from vast areas around them and accelerating galaxy formation far faster than ordinary star formation. Asterisk. Each of these explanations has its own validity. Each has been studied in detail. However, none fully explains everything we observe to date. There is a fourth category of explanation, and this is the most unsettling. Asterisk. What if the problem isn't our understanding of galaxies, dark matter, or the first stars? Asterisk. What if the problem lies in time itself? Asterisk. This isn't a marginal idea, but it might seem so. It's a serious scientific question carefully and humbly posed by researchers studying the deep structure of the cosmos. Asterisk. The age of the universe, 13.8 billion years, is not something we directly measure. This is a conclusion we've drawn from the expansion rate of space, the temperature in the cosmic microwave background, and the distribution of matter on massive scales. These measurements are incredibly precise. They've been refined over many years of observations from satellites, telescopes, and all sorts of surveys. They tell a consistent story. Asterisk. But what if there's a subtle flaw in that story? What if our interpretation of how light stretches across cosmic distances in the universe, the redshift we use to place galaxies in times, systematically, more or less, wrong? What if the expansion rate of the universe was different in very early times than our current models assume? A small difference in expansion history could shift the acquired ages of early galaxies by hundreds of millions of years, enough to resolve some of the discrepancies. Asterisk. Some researchers have also suggested that the laws of physics may have been slightly different in the early universe. Not vastly different, the same general framework, but slightly different in a way that would alter the rate of cosmic evolution, the speed of light, the gravitational constant, the fine structure constant that determines how matter and radiation interact. These are assumed to be universal and constant. However, there are some theoretical frameworks that don't represent fixed values. These frameworks belong to a cosmos that, in its very beginning, continued to learn its rules. And then comes the most speculative possibility, that the Big Bang may not have been an absolute beginning. Some cosmological models suggest that what we call the Big Bang was a transition, a jump in a long series of cosmic cycles, each collapsing and expanding, leaving traces in the cycle that followed. If such a cyclical universe is real, then the structures we find in the early universe may carry information from the previous cycle, not traces that are precisely preserved and not passed through by a cosmic jump, but encoded in density fluctuations and large-scale patterns that our universe inherited at the moment of its birth. Asterisk. This is definitely speculative. It's difficult to test, but it's an idea that is seriously considered, and the improbable galaxies found by the JWST lend new weight to this idea. Asterisk. Because if something existed before the Big Bang, if patterns from a previous cosmos were put in place at the moment of our transition, then what we see at the boundaries of time may not be so early after all. They may be older than our current understanding of cosmic age, Let's step back from the details for a moment and consider what all this means. Asterisk. Science is not simply a collection of information. It is a story we construct from evidence, a constantly revised, never-ending narrative. The Standard Model of the universe offers a wonderful story. It begins with the Big Bang, traces the formation of matter, describes the emergence of structure from virtually nothing, and lays out the universe we observe today with extraordinary precision. This is one of the greatest intellectual achievements in human history. But every story has gaps, places where the evidence is scarce, where the narrative omits details we haven't yet figured out. For many years, these gaps were so small that we could fill them with plausible assumptions and move on. The story held together. Improbable galaxies in the early universe reveal an irreparable gap. How the early cosmos was structured, the transition from hot, smooth plasma to complex, massive galaxies is not fully understood by our current perspective. The galaxies are still there, all of them, ancient, burning, cold, and alive, slowly turning their stories within the fabric of space. Even those that shouldn't be there, shining at the limit of what light can carry. They have waited patiently for 13 billion years. They will wait a little longer as we understand them. Asterisk. And now, as the music fades and the questions quieten, let go. Not backward, but forward into the space between understanding and wonder. Where the best science always begins. Asterisk. Allow the darkness to gently envelop you. Allow the stars to blur and soften. Let this entire impossible, magnificent, infinitely astonishing universe now be just a warm hum in the distance. There is a certain loneliness to being one of a kind. Asterisk. In science, if a single observation defies all expectations, the first reaction, the correct reaction, is skepticism. A single odd point of data doesn't destroy a theory. Yes, it raises a question. Sure, it causes reconsideration. But a theory built on thousands of observations is not destroyed by one extreme point. It is pursued, tested, and usually found to be alive. That's how the first impossible galaxy was approached. When the initial data arrived, this ancient, massive, fully formed structure shining at the edge of time, the community's reaction was cautious. Papers were written. Rigorous analyses were performed. Reasonable alternative explanations were offered. Perhaps the mass was exaggerated. Perhaps two overlapping objects were mistaken for a single object. Perhaps a small error in the redshift measurement placed it at the wrong point in cosmic history. Asterisk. These are not reasonable reactions. They are correct reactions. Science is a field where it should be difficult to be surprised. Asterisk. But then came the observations that followed. Asterisk. The same deep field, examined at different wavelengths, with different instruments, showed the same characteristics of the same object. The mass remained constant. The redshift remained constant. The star formation rate remained constant. The chemical richness remained constant. The object was real, and it was as it appeared. Asterisk. And then, over the years, others began to appear. Asterisk. Initially, not many. 2, then 4, then 8. Each was slightly different. Some had more mass, some had greater chemical richness. Some were still actively forming stars. Some had long since become dormant, but they all shared a fundamental impossibility when they existed. They were far too advanced for the age of the universe. Asterisk. The loneliness associated with the first anomaly transformed into something more unsettling. A pattern, a population, a class of objects that our best models never predicted and couldn't fully explain. Even retrospectively, asterisk, a single anomaly is a mystery. A population is a crisis and, approached with the right perspective, also an invitation. Now let's spend a few quiet minutes considering how we know this information. Because it's easy to talk about ancient galaxies billions of light years away, as if we could look at them. The reality is more complex and more magnificent. Asterisk. Everything we know about distant objects in the universe, everything, without exception, comes from light. Asterisk. Not from visiting them. Not from sending probes. Not from any direct measurement involving physical contact or proximity. Just photons, The smallest particles of electromagnetic radiation are particles of light that travel through space for millions of years, finally reaching our telescopes after an unimaginable journey. Each photon carries information. Its wavelength tells us about the energy of the process that produced it. Its direction tells us where it came from. And critically, how much the wavelength has stretched tells us how long it has traveled, how much the universe has expanded since it was emitted. The final point is redshift. As the universe expands, the area through which light travels grows with it. The wavelength of light stretches, shifting towards the red spectrum. The more redshift a photon undergoes, the older it is, the further back in time the object that produced it is. When we measure the redshift of a galaxy, we're not just measuring distance, we're also measuring time. We're looking back. Every deep-field image taken with the Hubble or Webb Space Telescope is a portrait of the past, and the further back you look, the further back you see. Beyond redshift, a galaxy's light spectrum reveals extraordinary detail. The presence of specific spectral lines, emission and absorption characteristics at particular wavelengths, tells us which elements are present and in what quantities. It indicates the temperature of the gas. It tells us whether stars are being born. It tells us whether the galaxy harbors an active supermassive black hole at its center, and whether it is pumping energy outwards. From a trail of light, too faint to be seen with the naked eye. At about half the distance of our eye, we can read a complete biography. We can learn how old the stars are, what they are made of, how quickly new stars are being born, and whether the entire system is growing or dying. To understand why these galaxies in the universe fascinate us so much, it's important to know the architecture of the universal structure, the fundamental structures upon which galaxies are built. We live in a universe shaped by dark matter. Dark matter doesn't emit light. It doesn't absorb light. As far as we know, it doesn't interact with electromagnetic waves. We can't see it directly at any wavelength with any instrument, but our confidence in its existence stems from the fact that its gravitational effects are clearly evident. The way galaxies rotate wouldn't make sense without the vast halos surrounding them, containing far more mass than the observable stars and gas. Galaxy clusters bend and distort the light of objects behind them. Through gravitational lensing, the amount of lensing indicates far more mass than visible matter. Currently, the best estimate is that dark matter makes up about 27% of the universe's total mass energy content. Normal matter, everything we touch, see, or build in our lives, consisting of protons, neutrons, and electrons, makes up only about 5%. The remaining part is dark energy, the mysterious force that accelerates the expansion of space. Dark matter was the first element of the structure. Before the first stars formed, before the first hydrogen clouds collapsed, dark matter had already begun to aggregate under gravity. Small density fluctuations in the early universe, quantum variations in energy distribution during the inflation period set the stage for the formation of these first dark matter halos. First, small halos formed, then merged with larger ones. The network of cosmic filaments and voids we observe today, where galaxy clusters are concentrated at the intersections of vast dark matter filaments, separated by enormous voids, is the mature form of these initial small fluctuations. Normal gas fell into these dark matter halos and cooled, condensing. Where the gas cooled and condensed, stars formed. Where enough stars came together, galaxies grew. This process, called hierarchical structure formation, is a well-known and tested process on large scales. At the level of galaxy clusters, superclusters, and the cosmic web, simulations are quite consistent with observations. But the problem arises at the level of individual galaxies, particularly in the earliest periods of cosmic time. Our models simulating how dark matter halos formed and merged in the early universe don't capture halos large enough to hold galaxies as large as those found by JWST early enough. Condensed dark matter pits, capable of accumulating so much gas and igniting so many stars, shouldn't have existed yet. But somehow, they did. And how what happened in the early universe that our models can't capture is one of the most defining puzzles of modern cosmology. In the spaces between the stars of these ancient galaxies, in the cold molecular clouds, where new stars are born, and the sparse hot gas in between, there is an unimaginable silence. Not the silence of an empty room, nor the silence of a quiet night. The silence of distances, the silence of voids. On such vast scales, that even light traveling at 300,000 kilometers per hour takes millions of years to traverse them. The average distance between stars within a galaxy is measured in light. Our nearest stellar neighbor, Proxima Centauri, is about 4.2 light-years away. The light you're currently receiving from it traveled 4 years ago. In those 4 years, that light traveled a distance so vast that even the fastest spacecraft ever built would have taken tens of thousands of years to traverse it. And that's a close neighbor. The stars in those ancient galaxies of the universe are separated by similar distances, and the galaxies themselves are millions and billions of light-years apart. The universe, despite all its wonders, is mostly empty space. But in that emptiness, something incredible happened. In regions that were only slightly denser than their surroundings, gravity gently stretched across that entire distance, gathering matter together. Initially, slowly, cosmically slow, over millions of years, and then faster, as the accumulated mass grew, and the gravitational effect deepened. The gas cooled. The clouds broke apart. Stars began to burn in hundreds, thousands, billions, and somehow, in the early universe, this process happened much faster than expected. The silence between the stars of these ancient galaxies is the same silence we've always known. The distances are the same. The physics are the same. But there was something about how those stars made a difference in the conditions that made it possible. We listen to that silence, trying to understand what it tells us. When astronomers examine the light of a galaxy in detail, they don't see a uniform glow. They observe the combined light of billions of stars, each adding its own wavelength signature. Each star tells a part of the galaxy's story. Stars, like people, age, and like people, their age is visible. Young stars burn hot and bright. They are large and blue, radiating energy at an enormous rate. They don't live longer a few million years for the largest and billions of years for smaller stars, like our Sun. In the spectrum of a galaxy with active star formation, blue-white light predominates. When you look at the bright arms of a spiral galaxy, you see young stars. Older stars, on the other hand, are cooler, redder, and smaller. They have burned regularly for billions of years and have slowly exhausted their hydrogen fuel. They add a warm orange-red glow to the galaxy's combined light. An elliptical galaxy, devoid of new star formation and filled with old stars, shines with this older light. By analyzing the combined spectrum of a galaxy's stars, the relative amounts of blue and red light, the specific absorption characteristics of different types of stars at different evolutionary stages, astronomers can construct a model of the star population. This model, in statistical terms, provides information about the stars' ages, compositions, and when their major star-forming periods occurred. Applying this analysis to the improbably early galaxies made the situation even more complex. Many of these galaxies showed mixed populations of both young, hot, recently formed stars and much older, cool stars that had formed much earlier. Even the presence of old stars was surprising. For old stars to appear at a time when the universe was less than 1 billion years old, they would have had to have formed extremely early within the first few 100 million years of cosmic history. Furthermore, they would have had to go through many cycles of stellar birth and death to enrich the surrounding gas with heavy elements. Some of these galaxies appeared to have star populations comparable in age to the oldest stars we know in our own galaxy, stars that formed in the early Milky Way more than 12 billion years ago. But these early universe objects existed at a time when 12 billion years hadn't yet passed. It was like being given a 500-year-old tree ring sample from a forest planted only 100 years ago. Simulations of the universe are one of the most ambitious computational projects in the history of science. One of the most challenging and important aspects of modeling galaxy formation is the feedback process. Stars are not passive objects. They are like energy-producing engines, and this production affects everything around them. A newborn star emits light that heats the surrounding gas. This can trigger the collapse of nearby gas clouds to form new stars, or it can add heat that prevents collapse. When a massive star reaches the end of its life and explodes as a supernova, it releases energy in seconds equivalent to the sun's total light production over 10 billion years. That explosion sends shockwaves into the surrounding galactic medium, compressing nearby gas clouds, potentially triggering new star formation, or even pushing gas out of the galaxy altogether. Supermassive black holes at galactic centers are even more dramatic in terms of feedback. When they actively pull in gas, when material falls in, heats up, and spirals energy toward the event horizon, they can produce jets of radiation and particles stretching hundreds of thousands of light years. These jets can heat the gas in a galaxy cluster, preventing it from cooling and new stars from forming. This process is called AGN feedback, and it's thought to be responsible for halting star formation in the largest galaxies. In the early universe, all this feedback operated under conditions we've never directly observed. The gas was denser. The radiation environment was more extreme. The first supernova explosions were different from the stars we see today. The geometry of the first galaxies, dense, compact, and wavy, was different from the established spirals and ellipses we observe today. Our feedback models are tuned to what we can observe. The easiest thing we can see is the universe as it is today, having evolved over billions of years. Applying these calibrated models to the early universe is an estimate, a reasonable estimate, carefully made, but it's still an estimate. The near impossible existence of early galaxies might be telling us that some of these estimates are wrong, that the feedback in the early universe was different, perhaps weaker in some conditions, allowing for faster star formation, while in others it was stronger, producing more dramatic arrest events. The details are extremely important. These simulations are remarkably successful in many respects. They impressively reproduce the large-scale structure of the universe, the cosmic web filled with filaments and voids. They generate galaxy populations, and the general characteristics of these galaxies are in remarkably good agreement with the count of galaxies we observe today. They have been an invaluable tool in testing our understanding of how the structure grew and evolved. However, once the JWST data arrived when the count of large, mature galaxies in the early universe was made, the simulations fell short. A very serious shortfall. The number of large galaxies found by the JWST in the first billion years of cosmic history was far greater than predicted by even the most optimistic simulations. The largest of these objects, those that were equal in mass to or greater than the Milky Way, when the universe was less than 600 million years old, were absent from the simulations. Even pushing the limits of the models couldn't produce these galaxies. Theorists worked hard. They concentrated the first dark matter halos. They increased star formation efficiency. They adjusted feedback parameters. Each change contributed, however small. But the difference didn't disappear. The result was unsettling, but inevitable. The simulations weren't just missing some galaxies. They were also overlooking an entirely different mode of galaxy formation, some process, or set of processes, that occurred in the early universe that the models failed to capture. That's how science progresses, not by finding that old answers are wrong, but by discovering that they are incomplete, by understanding that the universe holds more than we thought. One of the most important and challenging aspects of modeling galaxy formation is feedback. Stars are not passive objects. They are energy-producing engines, and that energy affects everything around them. A newborn star emits light that heats the surrounding gas. This can initiate the transformation of nearby gas clouds into other stars, or it can stop them by adding heat that prevents collapse. When a massive star reaches the end of its life and explodes as a supernova, this explosion releases energy equivalent to our Sun's total light output over 10 billion years old in just a few seconds. This explosion propagates shockwaves into the surrounding interstellar medium, compressing nearby gas clouds, potentially triggering new star formation and ejecting gas from the galaxy. Supermassive black holes at galactic centers are even more dramatic in terms of feedback. When they actively begin pulling in gas as material falls in, heats up, and releases energy in a spiral orientation toward the event horizon. They can produce jets of radiation and particles, stretching hundreds of thousands of light years. These jets can heat the gas in a galaxy cluster, preventing the formation of new stars. This process is called AGN feedback, and it's thought to be responsible for terminating star formation in the largest galaxies, in the early universe. All this feedback operated under conditions we hadn't directly observed before. The gas was denser. The radiation environment was more extreme. The first supernova were quite different from the stars we see today. The geometry of the earliest galaxies, dense, compressed, and turbulent, differed from the nearby established spirals and ellipses. Our feedback models have been adjusted to the data we can observe. And the easiest thing we can observe is the universe we see today. A universe that has evolved over billions of years. Applying these calibrated models to the early universe is an estimate. A sensible estimate, carefully made. But still an estimate. Impossible early galaxies may be telling us that some of these estimates might be wrong. That the feedback in the early universe was different, perhaps weaker in some cases, allowing for faster star formation, or stronger in others, producing more dramatic pause events. The details are extremely important, and with JWST we are now getting data that will delineate those details. Let's broaden the perspective for a moment. Impossible early galaxies are extraordinary, but they aren't the only thing showing that the dinosaurs is stranger and more capable than our models predict. Consider the case of supermassive black holes. We now know that almost every large galaxy has a supermassive black hole at its center. Our Milky Way has one Sagittarius A, about 4 million times more massive than the Sun. Giant elliptical galaxies at the centers of large clusters host black holes billions of times more massive. These objects are thought to grow slowly through gas absorption and collisions with smaller black holes. However, JWST has found black holes that were already enormous hundreds of millions of solar masses in the early universe. This happened when the universe was only a few 100 million years old. It takes a long time to grow a black hole to that mass through normal absorption. A lot of time, more time than was possible at that time. There's a reason these questions feel personal. They concern objects billions of light years away and billions of years ago. The atoms in your body formed in stars. Hydrogen, the most abundant element in the universe. The simplest atom, the first atom formed after the Big Bang, has been there since the beginning. It's a primordial matter. When the universe was just 3 minutes old, it began to exist in various forms. But the heavier elements, which forms the basis of every organic molecule, the oxygen you breathe, the iron in your blood, the calcium in your bones, none of these existed in the early universe. They were created later, inside stars. They were formed in the nuclear furnaces of stars, through nuclear synthesis processes that allow ordinary hydrogen to transform step by step into heavier elements. When a star dies, especially a giant star that dies violently as a supernova, it scatters these elements into space. They drift in molecular clouds, incorporating into new stars and their planets, and in some cases, resulting in life forms. In reality, as a temporary arrangement of atoms, you are the atoms that once existed inside stars. The iron in your blood was produced in the cores of a star that exploded billions of years ago. The carbon in your DNA was formed in a red giant gently shedding its outer layers into space. You are a universe temporarily arranged into a form capable of thinking about itself. Asterisk, in the context of this story, the improbable early galaxies are important because they provide information about the first cycles of this process, the first generation of stars that formed, burning and dying, enriching the universe with the elements necessary for planets and life to be possible. If these first cycles occurred faster than we think, if the early universe was more efficient, energetic, and creative than our models assume, the raw materials necessary for planets and life were available earlier than expected. Asterisk. The story of when life might have arisen in the universe is closely tied to the story of when the heavy elements were first produced. And the improbable early galaxies push that story back to the past, to the beginning. In the peaceful silence of these late hours, it's a nice pause to dwell for a moment of awe at the machines that made it possible. Asterisk, the James Webb Space Telescope, conceived in the late 1980s, was designed and built over 2 centuries by teams of more than 200 scientists, engineers, and technicians. It launched in December 2021 and is positioned 1.5 million kilometers from Earth. In a gravitationally stable location, its main mirror is 6.5 meters wide and composed of 18 hexagonal gold-plated beryllium segments designed to unfold like a giant origami flower in space. Its instruments are cooled to near absolute zero temperatures so they can detect even the weakest infrared signals. Asterisk, everything about its construction involved solving problems never before encountered. The mirror's folding mechanism, the unfolding of the 5-layered sunshield, thinner than a human hair, to keep the telescope operational, and the calibration of the instruments, which must function perfectly in the vacuum of deep space far beyond any possibility of manual repair. Asterisk, in many ways, it is the most complex scientific instrument ever built. Asterisk, and as it turned to the sky, to the dark areas between the stars, regions that previous telescopes had only vaguely observed, it saw the early universe in detail never before achieved. Galaxy after galaxy, billions of light years away, its light redshifted to the point of being almost unrecognizable, but captured and resolved with JWST's extraordinary sensitivity. Asterisk, before JWST, cosmologists could see clues to improbable early galaxies from the Hubble Space Telescope and ground-based observatories, clues, suggestions, statistical anomalies. But JWST transformed those clues into clear identifications, suggestions into catalogs, anomalies into a population. Asterisk, the questions we can ask, the mysteries we can investigate are always limited by the tools we have, and as we build better tools, the universe opens itself up to us more. Asterisk, every time we build a better telescope, the universe surprises us. Every time, absolutely. Asterisk, JWST is no different. Some regions of the universe are places we will never see. The observable universe, the sphere of space whose light has traveled long enough since the Big Bang to reach USA's, approximately 46 billion light-years wide. This is larger than 13.8 billion light-years, because space is expanding as light travels. Asterisk, beyond that boundary lies more universes, much more, almost infinite. But we cannot observe them because light from those regions has not reached us and never will. Because the expansion of space means that these regions are receding faster than light is traversing the increasing distance. Asterisk, in a sense, we are surrounded by a cosmic horizon. This is a limitation, not of space itself, but of the limit of our observational reach. The universe beyond that boundary exists, but we are infinitely far from it. Asterisk, it is strange and somewhat humbling to contemplate this situation. We study the universe with great precision, develop complex theories, build perfect telescopes, but all of this applies only to a part of the universe we can see. The rest, everything beyond our horizons, simply doesn't exist for us. Asterisk, and we can only see back to a certain point within our observable universe. The cosmic microwave background, the oldest light we can detect, comes from about 380,000 years after the Big Bang. Before that moment, the universe wasn't transparent. Light from those earliest times, if it can be called light in the usual sense, cannot reach us directly. Asterisk. We read the early story of the universe as if the first few chapters of a novel were torn off. From the context of the later chapters, we can deduce what they are probably saying, but we can't read them directly. Asterisk. These improbable early galaxies are, in a sense, the oldest pages we have. They formed when the universe was very young within the first billion years, and their light has been traveling toward us ever since. When JWST detects them, it is reading the oldest accessible chapters of the cosmic story. Asterisk. And those chapters don't speak as we expect. It's too late now. The day is over. The questions that preoccupied our minds while we were awake have quieted down. Now is a good time for slow thinking to allow ideas to circulate in the mind without waiting for a resolution. Asterisk. The universe began. In some ways, in the sense that our laws of physics can define it, there was a moment when the universe in its present state ceased to exist and then began to exist. Whether this was a true beginning, a transition to an earlier state, or whether the concept of before can be applied to the birth of space and time, is a question science is still seeking to answer. Asterisk. From that beginning, the universe began to expand and cool. Matter formed. Gravity, stretching over the cooling plasma, slowly began to structure it. In hundreds of millions of years, the first stars began to shine. The first galaxies coalesced, the first heavy elements melted and dispersed. And for billions more years, these processes continued. More complex structures, richer chemistries developed, and, eventually, on a small rocky planet orbiting an ordinary star, life emerged. And some of those life forms developed consciousness, curiosity, and the ability to look at the sky and question where everything came from. Asterisk. This is an astonishing story in its own right. Even before the first improbable galaxies, even before the JWST, even if our current models were perfectly accurate. Asterisk. The fact that the universe is more mysterious than we thought, that its early stages were more active, more productive, and more astonishing, doesn't diminish the story. Rather, it adds depth to it. Asterisk. Every mystery is an invitation. Every anomaly is a question. Every improbable galaxy, shining at the limit of what our telescopes can see, reminds us that the universe wants to show us more than we can imagine. Scientists spend much of their careers contemplating what they don't know. This isn't a lack of knowledge. It's the practice of science. Asterisk. A field where everything is known has ceased to be a field. It has become a catalogue. The dynamics of a scientific field come from its boundaries, from questions that don't yet have answers, from observations that don't fit existing models, from anomalies and inconsistencies that point to something new. Asterisk. Cosmology is incredibly alive right now. Asterisk. The first improbable galaxies aren't the only anomaly. There is also the Hubble tension, the fact that two independent methods of measuring the expansion rate of the universe produce slightly different values and stubbornly refuse to reconcile them despite large improvements in measurement accuracy. Some cosmologists think this is a systematic error, a subtle flaw in an as yet undetermined measurement method. Others argue that it points to new physics, that the expansion history of the universe is more complex than our standard model assumes. Dark energy is also a mystery. What drives the accelerating expansion of the universe? We know it exists because the expansion of space is accelerating, whereas only gravity should be slowing it down. But we don't know what dark energy is. Perhaps it's a constant property of space itself, the cosmological constant that Einstein introduced but then denied. Or it could be a dynamic field that changes over time. Or perhaps it's a reflection of new physics on the largest scales. We don't know what it is. Asterisk. Of course, dark matter also exists. We are certain of its existence. We have mapped its distribution in the universe through gravitational lensing and galaxy rotation curves. But after decades of searching through particle physics experiments, deep-seated direct detection experiments, astronomical observations, we have been unable to determine what dark matter is. What particles make it up? Why does it have mass but doesn't interact with light? Where did it come from? Asterisk, these mysteries, the elusive early galaxies, the Hubble strain, the nature of dark energy, the identity of dark matter, are not separate problems. Perhaps they are interconnected. They may all point to the same gap. The missing piece we're trying to understand. Asterisk, the very form of what we don't know, is informative. It shows us where to look. Cosmology is currently an extremely important field. Asterisk, impossible early galaxies aren't the only anomaly. There's also the Hubble tension too. Independent methods for measuring the expansion rate of the universe consistently, yielding different results and failing to agree. Despite significant advances in measurement accuracy, some cosmologists believe this is a systematic error. That is, a subtle flaw in a measurement method yet to be identified. Others believe it points to new physics, suggesting that the expansion history of the universe is more complex than our standard model assumes. Asterisk, then there's the mystery of dark energy, an element driving the accelerating expansion of the universe. We know it exists because space is expanding, and gravity alone is accelerating it when it should be slowing it down. But we don't know what dark energy is. Perhaps it's a constant property of space itself, like the cosmological constant introduced by Einstein but later rejected. Perhaps it's a dynamic field that changes over time. Or perhaps, on the largest scales, it's a manifestation of new physics. We have no idea yet. Asterisk, and of course, dark matter itself exists. We are certain of its existence. We have mapped its distribution in the universe through gravitational lensing and galaxy rotation curves. But after decades of searching particle physics experiments, underground direct detection experiments, astronomical observations, we still haven't been able to determine what dark matter is, what particles it's made of, why it has mass but doesn't interact with light, where it came from. Asterisk, these mysteries, impossible early galaxies, the Hubble strain, the nature of dark energy, the identity of dark matter, are not separate problems. They may be interconnected. All these situations may point to a gap in our understanding, a missing piece in the picture we are trying to build. Asterisk, the very nature of what we don't know is informative. It tells us where to look. 13 billion years from now, if something like human consciousness still exists, if the concept of observation still makes sense, what will the night sky be like? Asterisk, the universe will have expanded enormously. The galaxies we can observe in our current local group Andromeda, the Magellanic Clouds, the dozens of dwarf galaxies gravitationally bound to our galaxy, will likely have merged with us, forming a single large elliptical galaxy. But the more distant galaxies, those receding from us at speeds even light cannot track, will have vanished completely beyond our cosmic horizon. From the perspective of our distant counterparts, the night sky will appear darker and more isolated. The visible universe will contain fewer objects. Asterisk, the stars of our merged galaxy will still be there, but many of the largest and brightest will have long since faded, leaving behind neutron stars and black holes. The remaining stars will be cooler, smaller, and redder. New star formation will have slowed considerably as the cold gas is slowly consumed. Asterisk, this is a long future cooling, expanding. The universe is moving toward entropy, the diffusion of energy, the gradual fading of structure toward equilibrium. Asterisk, but we are not there yet. We are still very far off. Asterisk, right now, the universe is in its middle age of extraordinary richness. Galaxies are still forming, stars, clusters are still forming. Life, at least somewhere we know of, has emerged and is looking out at the sky. The light from those impossible early galaxies, sent forth when everything was just beginning, continues to arrive, carrying its ancient messages. Asterisk, the secrets of the early universe are finally becoming accessible to us. Light that has traveled for 13 billion years is finally falling into the instruments we have created to receive it. Asterisk, this is a wonderful time to be alive. Cosmology is currently an extremely important field. Asterisk, impossible early galaxies aren't the only anomaly. There's also the Hubble tension too. Independent methods for measuring the expansion rate of the universe consistently, yielding different results and failing to agree. Despite significant advances in measurement accuracy, some cosmologists believe this is a systematic error. That is, a subtle flaw in a measurement method yet to be identified. Others believe it points to new physics, suggesting that the expansion history of the universe is more complex than our standard model assumes. Then there's the mystery of dark energy, an element driving the accelerating expansion of the universe. We know it exists because space is expanding, and gravity alone is accelerating it when it should be slowing it down. But we don't know what dark energy is. Perhaps it's a constant property of space itself, like the cosmological constant introduced by Einstein but later rejected. Perhaps it's a dynamic field that changes over time. Or perhaps, on the largest scales, it's a manifestation of new physics. We have no idea yet. Right now, the universe is experiencing a period of extraordinary richness. Galaxies are still forming, new stars, clusters are still forming. Life in a place we know has emerged and is looking out at the sky. The light from ancient galaxies, spread out in the moments when everything first began, is still coming, carrying its ancient messages. Right now, we are in a time when the secrets of the early universe are finally being revealed to us. Like light, finally reaching the instruments we have built for ourselves. After a journey of 13 billion years, it's a wonderful time to survive. You've come a long way tonight. You've gone further than any ship could take you, to a place nobody could reach. You've explored places only your attention could reach, beyond the spiral arms of the galaxy. Beyond local groups, beyond the great galactic wall that marked the limits of what ancient telescopes could reach, and to the edge of the observable universe, where the oldest light and the deepest questions reside. You sat with the strangeness of a universe where everything evolves too quickly, a universe that creates things that shouldn't exist, a universe that stubbornly and magnificently resists our own narratives. That's the nature of reality. It's always more than our theories. It's always richer than our models. At its limit, it's always full of surprises. If you accept this, you can find peace within yourself. Tonight, you don't need to solve the mystery of impossible galaxies. You don't need to balance Hubble anxiety, identify dark matter, or understand the full nature of the Big Bang. Those questions will be here tomorrow. They will exist in some form 100 years from now, perhaps, replaced by deeper and stranger questions as each generation opens new horizons. What you can do right now is relax by accepting that the universe is a beautiful, deep, and still largely unknown place. Knowing that every star you see on a clear night is a story, a nuclear fire burning at the center of a system that may contain planets, clouds, weather, and seasons. Knowing that the light that reaches your eyes right now has traveled for years, decades, centuries, millions of years, patiently and silently carrying its own little cosmic knowledge, finally reaching you. You are a part of this story. You are not a passive observer, but a participant in it. The atoms that make up your body were once part of stars, clouds, and ancient seas. After you are gone, they will become part of other things. You are one of the fleeting patterns of the universe, short, improbable, and remarkable. Allow your breath to slow. Allow the edges of your thoughts to soften. Allow the impossible galaxies to fade away again, still shining, still patient, still carrying their mysteries. The night is silent. The universe is vast. And you are exactly where you need to be. Breathe now, slowly. The music will carry you away from the rest. Rest here, among the galaxies. Good night, sweet dreams.